In this screencast, we'll look at an important property of fluids, viscosity, which we designate with the Greek letter mu. And viscosity has units of Newton seconds per meter squared. And what we're going to do is determine its relationship to shear stress. So the typical definition of viscosity is a fluid's resistance to flow, or another way of putting it is internal friction. So remember that a fluid is defined as a substance that will deform continuously when a shear stress is applied. So you can understand why we might be interested in determining a shear stress and why viscosity is so important. So a shear stress is created whenever a tangential force, which we'll call F sub x, is acting on a surface, and the surface that we're looking at is A sub x. So this is basically a plate that looks like this, and that's its area. So we're going to consider a fluid that's placed between two parallel plates. So in this picture, the bottom plate right here is stationary, and the top plate moves with a velocity u that's due to this tangential force F that's applied to it. And that creates shear stress. However, be careful not to equate shear stress with tangential force. So shear stress is equal to this tangential force divided by this area that it acts on. So the fluid in contact with the top plate moves with the plate velocity, and again we call this u, while the fluid in contact with the bottom plate, because it's stationary, has no velocity. And this is what's known as the no-slip condition. In other words, the fluid sticks to the solid it's in contact with. So since the velocity at the top is u and the velocity at the bottom is 0, there must be some kind of velocity gradient, which we call du dy. So here, if you look at it, the profile, the velocity profile is linear. In other words, u of y is equal to u, that big U, of the velocity of the plate, divided by h, which is the space between the plates, times y. However, we can have more complex velocity profiles, but in interest of showing you how viscosity and shear stress works, we're going to stick with a linear one. So in the figure, if you look here, L sub y right here is the moving distance of the fluid for a layer at some location y from the bottom plate. And that L is the moving distance of the top plate, F is the force, and again h is the distance between the plates. So what happens if we increase this force? What will happen is that u will also increase. Therefore, what's known as the rate of shearing strain, and you may often see it like this, which is equal to du dy, and in this case is equal to u over h, increases proportionally to the shear stress. In other words, this tau, which we call shear stress, is proportional to du dy. And this constant of proportionality is known as mu. Therefore, we can call the shear stress, tau, equal to mu du dy. So fluids for which the shearing strain is linearly related to the shear stress, that's what's known as Newtonian fluids. So what happens if the shear stress and the rate of shearing strain are not linear related? Then we have what are known as non-Newtonian fluids. So here, let's look at a graph of shear strain, du dy, versus shear stress, our tau here. So a Newtonian fluid, such as water or oil, you're going to have a line that looks like this. However, if we draw a line that looks like this, it's still linear, but the y-intercept, so we're going to write an axis like this, the y-intercept is not 0. So what it means is it takes a certain amount of shear stress, which we call the yield stress and is often designated by tau 0. We need that amount to create flow. So an example of this is ketchup. We also have what are known as shear thickening fluids, where the viscosity increases with increasing shear rate, such as this. And examples include quicksand or cornstarch and water, as well as shear thinning fluids, where the viscosity decreases with increasing shear rate. And an example of that is paint. So an understanding of viscosity is extremely important, not only because it's a fundamental property of a fluid, but also because it's part of what creates shear stress, and shear stress is what defines a fluid.